Hey, welcome back everyone. In this video we're going to take a close look at resistance. Now we previously calculated resistance and we looked at resistance when we started talking about conductors. But when we calculated resistance, we only calculated the resistance when we had an object that was uniform in cross-sectional area. And here we're going to look at non-uniform cross-sectional areas, how we can apply Laplace's equation to figure out the resistance of such an object. Let's take a look. I've got an example that we're going to work through, but before that, I just want to remind you of a couple things. So when we did look at resistance, we said that the resistance in ohms was the change in length of the conductor divided by its conductance times its surface area, like this. So when we say uniform conductor, what we mean is that the cross-sectional area of the conductor, A, I guess we used S in the video. Let me use S. We mean the cross-sectional area S is uniform, so wherever you slice it along the length, that it's going to be the same anywhere along the length. And it's got uniform conductivity, meaning the material is homogeneous. It's carbon, for example. It's just carbon. Carbon would have a conductivity that we can look up in a table. So we can use this equation. However, what we also saw, but we did not apply yet, was this equation. Resistance is voltage over current. And so what we can do alternatively is calculate the voltage with E dot dl, the integral, divided by the integral of a surface area, that cross-sectional area, E sigma E, which is the current density, times the ds, or dotted with ds. Right? This is V over I. If you integrate the current density over the surface area, then you have the total current that goes through the conductor. So again, we saw this previously, but we did not apply it. We're going to apply it here in this video. We're going to do that, and we're going to use a certain method. And I just want to write out that method to you so you'll be able to see it then in action in this example. So the first step to finding the resistance of a non-uniform object is to choose an appropriate coordinate system. Okay. So you can look at this figure that we are going to tackle in a second, and you can kind of think about what sort of coordinate system you would use for that object. Now, step 2, we're going to assume V0 potential difference across the material. Right, we don't want to plug in a number, but we'll say that it's known. And what's going to happen is that it will drop out of the calculation because V and I, as you'll see, will end up being proportional to V0. So we're just going to assume the voltage across the conductor is V0, and then what you're going to find is that the numerator is going to be V0, obviously, right? That's the voltage, but the denominator will also be proportional to V0, and so the V0s will cancel. So whatever number, we're not going to assume a number, but we're just going to call it V0. Whatever we assume for that voltage will drop out in this ratio, giving us the resistance. Okay, step 3. So we've assumed V0. So with V0, then we have the voltage at one end and the voltage at the other end. And so what we can do then is solve Laplace's equation. For the voltage everywhere, the potential difference everywhere in the material. Then we know we can get the electric field, which is the negative gradient of the potential difference. And then further, we can get the current, which is the surface integral of the current density, which is sigma times the electric field, dotted with ds, right? So we have those things. Then we've got the voltage. Voltage we've assumed is V0. Now we've got the current from step 3. So then we can calculate R is equal to V0 over I. And then we've got the resistance of the non-uniform object. All right, so I'm going to leave that up for now, and we're going to address this example now. So we've got a metal bar of conductivity sigma. So again, if we knew the type of material, like carbon maybe, we can look that up in a table and figure out what sigma is. Some books have it in the appendix. So this material is bent to form a flat 90-degree sector of inner radius A and outer radius B and thickness T. Show that the resistance, so we'll do part A first, of the bar between the vertical curved surfaces. So between A, that surface there that's curved at A, and the surface that's curved at B, find the resistance, show that the resistance between A and B is this thing, 2 natural log B over A over sigma pi T. Let's get started. So I look at this thing and I see that one dimension is rectangular. The thickness of it is not curved, it's rectangular. But then I see other dimensions are curved. And so I conclude that cylindrical coordinates would be a good choice here. So that's step 1, cylindrical coordinates. And if I choose cylindrical coordinates, then I can describe my object very easily. Notice that the radius, or the rho coordinate, goes from A to B. The phi coordinate goes from 0 to pi over 2, right? 0 with the x-axis, and then pi over 2 would be the y-axis. And then further, z goes from 0, if it's lying on the xy plane, to t. And I also, actually, before we continue, I want to point out that maybe this figure is not given to you, and so you have to decide how to orient the object, right? So really step 1 is choose a coordinate system and orient the object in an appropriate manner. So you don't want the object going through the origin, because then you'll have a mess. So you need to decide how to do that. Okay, now the potential then due to this thing, right? So if you've got a potential difference, well, I guess we'll set up that potential difference. So let's say that the potential at A, so surface A, that curved surface, is grounded, and you can choose either one to be grounded. So I'm just going to choose surface A to be grounded, and then I'm going to choose surface B to be at this V0 volts. Okay, you could do it the other way, certainly. But see, what we're doing here is we're assuming V0 across the material. So now the potential difference across the material is V0. Now notice the electric field, and thus the potential, is only going to be a function of rho. Then we have this rho symmetry. So we're talking an electric field then points along the rho direction, like this. All right, so that's nice. So if it only depends on rho, then Laplace's equation, so now see we have the boundary conditions now, V0 and ground. Laplace's equation then in cylindrical coordinates and in one dimension, in the row dimension, is this. Really that doesn't even need to be a partial because there's only one variable, rho. Okay, so we're on step 3 right now. We're solving Laplace's equation for V. So I have this, and I can multiply by rho. Right? We looked at several examples of solving Laplace's equation. So I'm going to multiply by rho, and this is still 0 then. Now I have the derivative of something, the thing in parentheses, is 0. So that means that something, that thing in parentheses, must be a constant. So I'm going to call that constant C1. Okay? Now I have rho times a derivative is a constant. So let me divide by rho. Like this. And so I have the derivative of something is 1 over rho C1. All right, so now let me integrate twice now. This is the second integration, and I get rho, or V, not rho, V is equal to, so the integral of 1 over rho is natural log of rho, and then I still have, I guess I'll put the C1 in front, C1 natural log of rho, and then I need a new constant of integration. We'll call that C2. So two constants for integrating twice in one dimension. Now we solve for these constants. You should be very comfortable with this process based on the previous example videos. So to get the boundary conditions then, or we plug in the boundary conditions, so the voltage at rho equals A, we're saying is 0. Right? And so if I plug in A here into my voltage, that gives me C1 natural log of A plus C2. And then if I plug in the other boundary condition, rho at B, that should be V0 volts, and so that is C1 natural log of B plus C2. So I have two equations and two unknowns. I need to solve those things for C1 and C2. Now the quickest way that I see to do this is to subtract the second equation, the first equation from the second equation. So if I subtract, then I've got V0 equals, the C2's drop out, and I've got C1, and then using a property of natural log, I get B over A. All right, and then I can plug, then I can solve for C1. Let me get C1. That would be V0 over natural log of B over A, like this. And then I can plug C1 into any of these equations and solve for C2. And I get C2 is negative V0 natural log of A over natural log of B over A. All right. So I'm going to erase some of this work. I'm going to erase this work over here. So with those constants, I can plug them back into our potential difference equation, therefore fully specifying the potential. And if I use a property of natural logs and so forth, I can get this thing as the voltage is equal to V0 times the natural log of rho over A. See, because what I'll have is the natural log of rho and minus the natural log of A once I factor these things out. So then I can use a property that becomes the natural log of rho over A, and then divided by the natural log of B over A. Okay, that shouldn't be a problem there. All right, so now with V fully specified, I'm going to give myself a little bit more room again. So I'm going to just delete that. Now I can get the electric field. See, we're just going through this process. I've solved Laplace's equation for V. Now I'm going to get the electric field. So let's recall that the electric field is the negative gradient of V. Now in in cylindrical coordinates, just in one dimension, this is nice. This is just negative dV d rho in the rho direction. Real easy there. So I take the derivative versus rho of V. So the derivative of natural log of rho is 1 over rho, right? And then we've got this negative. So the derivative here would give us negative V0 over rho natural log of B over A in the rho direction, like this. Good. So we've got the electric field. Now let's get the current going again, step by step here. I guess we're still on step 3. The current is the surface integral of the current density, which is sigma dot E, or sigma E dot ds. Right. All right. So let's pull out all the constants. So I've got a negative sigma V0 natural log of B over A times the surface integral. I've got 1 over rho, right, in the rho direction, dotted with the surface vector. So we need to think about the surface vector. So we're talking about changing in the rho direction. We're going from, the electric field goes from the B surface here, the outer curved surface, to the inner surface. So we're going in the rho direction. We ask ourselves, what is changing then? Well, we've got phi that's changing from 0 to pi over 2, and we've got z that changes from 0 to t, thickness t. And because we're going in the negative rho direction, we need a negative sign here. So I'm going to write negative rho d phi. So remember, the rho comes about because the phi is an angle. When phi changes, we have rho d phi. So there's rho d phi dz in the rho direction, like that. Early in the semester there, ds. Okay, so we do the dot product, and a rho dotted with a rho is 1, and notice the rho's cancel. That's good. The negatives cancel, and then we just end up integrating phi and z, and phi goes, as we said, phi goes from 0 to pi over 2, and z goes from 0 to t, and all these things are constants, and so we just get, here's the t from the integration of a constant, and then we have a pi, and then we need a pi over 2, right, from the phi integration, natural log of B over A, right? So that's the current. Okay, so now we're on step 4. Now the resistance is just V0 over I. Well, V0 over I. So when I do that division, notice the V0s drop out, right? That's what we said in step 2, that the V was going to drop out. And so we get the resistance is just 2 natural log of B over A divided by sigma pi t, right, when we do that division. Nice. All right, I'm going to erase that. I'm going to also erase the steps just to give me some more space. We're going to look at part B. So this was if we were to put electrodes on the A surface and the rho equals B surface. But we could alternatively do part B, where we attach electrodes between the two horizontal surfaces at z equals 0, so the bottom, this thing is resting on its bottom, right, and the top surface, z equals t. And so if we do that, now we want to show that the resistance is 4t over pi sigma b squared minus a squared. All right, let's do it. So now, I don't really want to, I can't erase this, so I'm just going to cross it out. But now I'll show in blue. We're going to ground the bottom, and then we're going to, on the top, suppose V0 volts. So now the electric field points like this in the z direction. Again, I can't erase the red arrows right now, but they're pointing down the material if we do that. So what we just said was then we're letting V0 equals 0. This is, let me back up. This is at z equals 0 is 0. And the voltage at z equals t, we're letting be V0 volts. So the potential is going to vary and the electric field is going to vary in the z direction now, because we're talking from z equals t to z equals 0. So Laplace's equation in one dimension in cylindrical coordinates just becomes d squared v dz squared equals 0. That's real nice. And you might notice that I've written derivatives instead of partial derivatives because we only have one variable, z. It's the electric field is not varying, or the voltage is not varying in any other direction. So we integrate once. We have the second derivative of something equals 0. So when we integrate once, we know that the first derivative must be a constant. And then when we integrate twice, we know that then the voltage has got to be C1 times Z plus another constant. Okay, so I've got to get those constants. So I apply the boundary conditions. At 0, I should have 0. So that gives me C2, actually. That's nice. So C2 is 0. And at T, I should have V0 volts. So that is C1 times T, right? And so that implies that C1 is V0 over T. So now our voltage, our potential difference, is fully specified. C1 is V0 over T, and then times Z, and then C2 is 0. Nice. Okay, moving right along then, the next step was to calculate the electric field. I'll do that over here. The electric field is the negative gradient of the voltage, or the potential difference. And in cylindrical coordinates, with just one variable, this is just minus d dz of v, and v is v0 over t times z in the z direction. All right, so we do that derivative. That's a straightforward derivative there. And so we have our electric field. Now the current is the next step. Current is the surface integral of the conductivity times the electric field dotted with ds. Remember, the conductivity times the electric field is the current density. So we're taking the current density, dotting with the surface, and integrate, and then that gives us the current. All right, so when we do that now, we can pull out the constants, minus sigma, V0, T, right? Those are all constants. And then from the electric field, we're just left with AZ, dotted with, now we need to talk about ds. So we're looking now in the z direction. And so in the z direction, we ask ourselves, well, what changes? Well, phi again changes, right, from 0 to pi over 2, And rho changes now. Rho changes from A to B. So our ds vector becomes negative rho d phi, and the rho d phi is due to the d phi changing, rho d phi, and then d rho is changing. And the negative here, I'm using it just to cancel with this negative here. If you didn't leave off that negative, then you would have a negative resistance, and you know that you need a positive resistance. So it's just kind of a little hand waving at this point, but you can just put your resistance as a positive number, because the way we're integrating isn't exactly clear if we're going to take rho going from A to B or rho going from B to A. All right, so az is 1. The negatives cancel, as I said, and then we've got to integrate rho, which is interesting. So this becomes sigma v0 over t. Rho goes from A to B, or from B to A. You'll just get a negative. Phi goes from 0 to pi over 2 over our material. And then we've got rho d phi d rho. Okay, so when I integrate over phi, this thing does not depend on phi, so this is just pi over 2. So this becomes sigma v0 pi over 2t times rho goes from A to B of rho d rho. And so when I integrate rho d rho, I get 1/2 rho squared. So that would make a 4 in the denominator. And then when I plug in the bounds, I get this over 4t, plugging in the bounds, b squared minus a squared, like that. Okay, I'm going to erase this. Now, we want the resistance, so we're on step 4 now. We assumed a potential difference of V0 across the plates, and now I take V0 divided by I, right? The resistance is V0 over I. So when I do that division, clearly the V0s drop out, and I'm left with 4t over sigma pi b squared minus a squared, which is what I was supposed to get at, and that's great. So that's our answer, and I do want to point out one thing. So I want to be very clear. We're done with the problem, but I want to show you or interpret our answer a little bit. For part B, and only part B, the cross-sectional area as you go in the z direction does not change. Imagine slicing this thing parallel to the z direction. The cross-sectional area does not change. The cross-sectional area is 1/4 pi b squared minus pi a squared. It's 1/4 because it's a 1/4 of a circle, and then we take, pi b squared would be the area of the entire quadrant, and then we have to subtract the pi a squared, which is the inside that's missing. So that would be the cross-sectional area of this thing. And again, as we go from 0 to t in the z direction, this area stays the same. Wherever you slice it, you're going to get a slice of that area. So that means that for part B, and part B only, this equation holds. This is how we started the video, remember? So that holds, and so the change in L, the change in the length is t, right? The thickness is t, and then divided by sigma, and then times the area. I guess we used s here. The area is this thing. So when I divide by that, the 4 comes on top, and we're left with, I can factor out a pi b squared minus a squared, and so I get the same answer. Nice. Okay, so that shows you how we can calculate the resistance of non-uniform objects. In the next video, we're going to talk about an equally important device or component in circuits, and that's the capacitor. We haven't even talked about capacitance quite yet. Although we did actually calculate some capacitance, we just didn't call it we looked at a capacitor. We just didn't call it a capacitor. So in the next video, we're going to apply a similar process, but we're going to calculate the capacitance of some objects. I'll see you then.